And so now that you can interpret the coefficients from this model, let's return back to the overall model summary once again. Run that once more. So now these estimates all make sense. The intercept, flake axis, and the denticulated notched pieces. These are just slopes for each of those different values, beta values for each of those. And of course, as before, they've all got standard errors, t-values, and p-values. Now, when you're interpreting a linear model, as I said before, you're not actually looking at the p-values here in this final column of the coefficients. Those p-values are simply telling you whether this estimate is significantly different from 0 or not. This is not telling you, for example, that the p-value for flake axis being different is 0.128. That's not at all what that means. That's a separate issue. You really won't be looking at these p-values all that often. The p-value that you actually care about is reported down below, here, the very bottom. P-value for this model is 0.033. That's a significant p-value, right? And so even though these p-values up here were not significant, right, the overall one is, because again, these p-values don't mean what you think they mean most often. It's just whether that estimate's significantly different from 0. So when you're interpreting this model and you see this significant p-value at the bottom, this is your model p-value. That's what really matters. It is significant at the 0.05 level. And so we can say that there is a significant difference in Easting coordinates between these three artifact types. This p-value means that there is only a 3% chance that we would get these data if all of these artifact types were distributed the same way across those Easting values. If their Easting values were all coming from the same kind of source, or therefore all distributed accordingly, it's only a 3% chance that we would get these data. So it's very unlikely that these data would occur if that null hypothesis were true. So we can reasonably reject that null hypothesis and say that there's a significant difference. When we're reporting the results of this model, we, as always, need the F statistic and the degrees of freedom. In this case, the F statistic is 3.586, so you would say something like F, and then in parentheses here we can put 2,67. Those are our degrees of freedom, and say that F equals 3.586. P is less than 0.05, because we have a significant p-value. It's significant at that level. So this is kind of the basics of interpreting this model. What this model actually is an ANOVA, an analysis of variance. This is another common type of statistical hypothesis test. Whereas a t-test that we discussed before is a linear model where your predictor variable takes 2 categorical values, and ANOVA is when it takes 3 or more categorical values. And so here, when we've compared the mean Eastings of 3 different artifact types, we've actually run an ANOVA. We did it in the form of the LM function using a linear model, because that's what it is. It's just another type of linear model, same as a t-test. And so with an ANOVA, you can also, the conventional way to do this is to take your LM object, which is barm mod, and you run the ANOVA function on it. And if I run that, I get actually the same output as the LM. I get that same p-value from above. I get the same f value there. We've got the degrees of freedom here, 2 and 67. And so this is just kind of a stripped down and simplified version where you don't get the estimates of the coefficients. You just get what matters most for reporting the result of this ANOVA, which is the f test statistic, your degrees of freedom, and your p-value. And so running kind of that barm, where barm mod is the object that we took our LM object and assigned it to, then you run ANOVA on that, and you've got your ANOVA results. So you can interpret these in the same way as we did before. It's just got less detail as the full linear model, but you'll see that it's basically the same thing. Now, R also has another function called AOV, which will run an ANOVA for you. If we were to use the AOV function, East as a function of label, again specifying the exact same thing as before. Easting is a function of the artifact type label from the BARM data object. And if we run this AOV function, which is the built-in ANOVA function in R, run that, and then inspect the summary of the object that we created, you can get the same thing. Again, we've got our p-value there, we've got the f value, the degrees of freedom, it's all there, same as before. Some people like this AOV function because it allows you to skip building a linear model and then running the ANOVA function. That's a two-step process, whereas this is really all wrapped up in this one AOV function, and then you just inspect the output of it to get your ANOVA. So, as I said, this type of linear model where you've got more than two, so three or more categories in your predictor variable, this is an ANOVA, an analysis of variance. But again, same as the t-test, even though it's got that fancy name, at its core, it's still just a linear model.